Hi guys, I'm Ari. I'm one of the moderators here at the conference. I'm going to be the technical co-host here, which basically just means if any of you guys are Zoom bombing, then I have the power to get rid of you. But I, outside of here, I work at a marketing agency for sustainable technology companies. I'm actually branching us specifically into the carbon tech space and have been for about a year or two. And then I co-run a volunteer organization called the Open Air Collective, which helps advance direct air carbon capture through policy initiatives and collaborative open source hardware research and development. So like, for example, we're building the world's first open source direct air carbon capture machine. So it's a little on me. I don't know if we're all the same order here. So I guess Canon, you're next on my screen. You want to do a quick intro?
Great, thanks. Yeah, this breakout session was suggested by our people. I'm Canon Bryan. I'm the Chief Financial Officer and co-founder of a company called Terrestrial Energy based in Canada. We are developing a commercial, advanced, small nuclear power plants for deployment for commercial deployment first in North America. And our corporate objective is to build and license nuclear power plants for under $1 billion USDs. So making the capital cost of a nuclear power plant comparable to a gas plant or a coal plant, and making it affordable for economies of any size and character, including smaller economies in Africa and Asia. So what I personally have a tremendous interest in carbon utilization, especially, and our high temperature nuclear drive has the capability of powering, providing the intense power which is needed for carbon capture, and also the intense power which is needed for the chemistry to separate carbon from its feedstock.
Ken, I just want to clarify. This is the group for the decentralized DAC conversation, everyone, or am I wrong on that part?
No, yeah. This is nuclear power DAC.
Yeah, this is nuclear.
Yeah,
Okay,
I think decentralized DAC is next round, right?
Yeah, I think that's right.
That's my bad. Sorry about that.
Because I was going to host that.
I'll be in that too.
One good thing about small nuclear is that it's decentralized. So
that too.
It can be anywhere, and it can be small scale. So you could have it on ships, in the ocean. You could have it on, trying to prevent all kinds of issues. So yeah, it's decentralized.
So quick question, Canon or Bryan.
It's Canon.
Canon. Yeah. Okay. Yes. What size are your molten salt reactors? Like how many megawatts?
Yeah, so our first commercial formulation is 200 megawatts electrical. It's based on a reactor system which is 400 megawatts thermal. So we have right-sized the system to address market needs. So we have an industrial advisory board with some of the largest electric utility companies in North America, and also one in Europe so far. And we work closely with these electric utility companies, and they provide market relevant information to us about what the market demands in terms of these formulations. But that's for electric. Obviously, that is for an electric power application. So, if this system were to be used for carbon to drive carbon capture, or to drive the chemical processing for carbon utilization, sequestration and utilization, then that may not require an electric power component. So, in other words, you could have a nuclear reactor, which is a high temperature system delivering high temperature to an industrial process, like chemical processing, for example, without the need for power generation infrastructure. So,
which is
you-
basically the most inefficient part of the reactor, right? So
Yes,
if
exactly.
you can sidestep that, then you're like, yeah, you're.
It's also
you're
tremendously
very-
costly. The power conversion equipment is up to 50% of the total capex. So if you can eliminate the need for that and use the heat directly in a chemical process, then you're really having the most efficient system you can possibly have.
Yeah, Canon, I understand the old-fashioned light reactors were always limited to about 300 C, which isn't that useful for chemistry and industrial processes. What temperature do you think you can provide heat output at efficiently?
Yes, thanks, Carl. Good question. It's true. Classics, traditional nuclear power plants, they're pretty much all the same all around the world. And they have a limitation of about 300, up to 300 C, 300 degrees C. And our molten salt reactor system, it gets up to, has an operating temperature of 700 C. It can deliver heat in the form of a hot molten salt at maybe 650 C. And of course, we can pretty easily and thermally efficiently increase that heat to, let's say, 850, 900 with so-called electrified top-up heat. So when you have a high temperature material already, of course, the thermal efficiency goes way up. So if you're trying to go from 100 to 900, well, that's pretty hard. But if you're going from 700 to 900, that's a lot easier and a lot less power intensive and a lot more thermally efficient.
So regarding like coupling this to direct air capture, probably the best chemical process you're looking on is the one of carbon engineering, since they require a higher heat. Like, for example, the system Klaus Luckner uses is just moisture swing, so that won't be applicable. Temperature vacuum swing usually is like 100 degrees Celsius. And then what carbon engineering does is basically they're carbon looping. So they're basically continuously looping between a carbonate and then breaking that up into quicklime and doing that back. And they need a temperature in the order of your temperature. So I think that would be the most interesting application.
Yeah, possibly, but the heat from the system can obviously be used in thermal applications, but most carbon capture systems that I'm aware of require an awful lot of power, and a nuclear reactor is a massive engine of power, particularly when you compare it to, let's say, a wind farm or a solar farm. And you know, the energy intensity of nuclear simply doesn't allow any other energy source to compete, and that includes fossil fuels as well, and hydro. So if you want to make carbon at scale, then a nuclear system is really the best way of doing it.
So has anyone in this group ever, so I know, for example, Carbon Engineering did this interesting paper in Joule, and they did different cost analysis of a natural gas fired direct air capture cost. It was like $94 per ton of carbon dioxide. And they also did one with renewable electricity. Did anyone do such a calculation with a molten salt reactor? Including like the thermal efficiency that you get extra.
Mm-hmm. Yeah, we're actually working on that right now. I don't want to provide any numbers that are likely to be wrong, so I'm just going to leave it at that. But let me say that at the minimum, we can do as well as natural gas in terms of delivering that heat.
And the extra
so as good as or better.
Yeah, and the extra.
So Canon, what is that process using heat to pull carbon from the atmosphere?
Oh, well, that depends on, that's not our area, right? That's up to the carbon capture companies to figure out those technologies. And you know, where we come in is simply providing the power, whether it's thermal power or electric power or combination of both.
What about the power cannon for creating hydrogen in order to get synthetic fuels from the actual carbon?
Well, so that's actually one of my favorite topics. I mean, as everybody in this conference knows very well, getting carbon is great, but then what do you do with it? I know there's been a lot of really terrific, innovative ideas about what to do with carbon. One of my favorite things to do with carbon is to mix it with, formulate it with hydrogen and make aviation fuel or other types of synthetic fuels. You can make these fuels drop-in substitutable, and carbon engineering is making these types of fuels. And I guess the point that we're trying to get across today is that you can make these fuels at far greater scale and far more thermally efficiently if you're using a high temperature nuclear system. This has never been available to industry before in history. This is the first time. So the world doesn't really know or comprehend how efficient these or how low cost these processes can get. So just doing some preliminary studies right now, we've figured out that we can, using our system and making hydrogen from water using high temperature steam electrolysis, which is a proven process, and getting carbon from the flue gas from a cement factory, we can make gasoline for around 26 cents per liter, 26 USDs, 26 US cents per liter. So we're in the process of getting these costs down. That's the whole point. Got to make these synthetic fuels cheaper than petroleum-based fuels. And once we do that, we think the world will be faced with an inevitable decision, which is, are we going to use petroleum-based fuels, which are very dirty and killing our planet, or are we going to use clean carbon neutral fuels that are actually cheaper? Not a difficult decision.
Hey, Canon, sorry, I wanted to jump in. I don't know a lot about advanced nuclear technology. Can you talk a little bit about power generation and any nuclear waste and handling that you guys are working on?
How do you mean by, I'm not sure exactly what you mean by power generation.
Well, what I'm really concerned about, what I'm really interested in is how does nuclear waste generated by the advanced process differ from what people learned about at 3 Mile Island and Chernobyl and elsewhere? What sort of storage and disposal problems do you have to solve?
Well, as it turns out, well, I'm from the nuclear power industry. I've been in it for 16 years, and the fact is, nuclear waste, so-called, which is actually unused nuclear fuel, that's what it really is has actually never created a problem anywhere for anyone. In 65 years and 19,000 reactor years of clean electricity, precisely 0.0 people have ever been harmed by nuclear waste, and precisely 0.0 ecosystems have ever been disturbed by nuclear waste from civilian nuclear energy. So we don't consider it a market problem. We're not trying, our company is out there to solve market problems. Conventional nuclear has a market problem, and it's not hot enough, and the capital costs are too high. Our job is to solve market problems. The market problem is we need to make the capex lower, and we need to make the temperature output higher. If we do that, we can participate in industrial markets, and the spent nuclear fuel is it can be dealt with in the way that it's being dealt with for the last 65 years, and that would be non-problematic in any way based on deterministic data, 65 years of deterministic data, or we can reprocess that unused nuclear fuel and use it and convert it into energy, trillions of dollars literally of new energy. So that's our that's our response to that.
So are you guys in collaboration with a direct air capture company?
No official collaborations, though we've had many unofficial projects that we worked on with carbon engineering. As it turns out, I live in Vancouver. Carbon engineering is based in Vancouver. And so we've presented together at conferences and you know, we've worked on some numbers together and we found out some very interesting things. I know the folks at Carbon Engineering pretty well, and they're great people and they've done an amazing job. And I truly hope that we could have a more formal collaboration at some time in the future when we start getting serious about synthetic fuel production.
Because I think like a lot of the checkbox are marked there. First of all, the temperature of their process is spot on with what you guys want, 674 degrees Celsius. You can make hydrogen at the same time. Carbon Engineering wants to make synthetic fuels, backed by Bill Gates, who is a huge nuclear proponent. David Keith, who also is thinking about creating these large-scale
and he has a PhD
fuels.
in physics as well.
Yeah, exactly. So yeah, I think it makes a lot of sense. Actually, I didn't really think, because from a direct air capture, so I'm working on creating a small modular direct air capture unit, and to me the high temperature direct air capture process seems very inefficient. The only way you want to do it is if you want to create this huge industrial setups and use or piggyback on existing industrial equipment, which is the route Carbon Engineering is taking. But I actually think in the case, it makes a lot of sense to combine this with salt and molten salt reactors. So I didn't connect this before. It's very interesting.
You know, of course, that there are some advanced reactor companies that are looking at much smaller units than what Terrestrial Energy is. So if you've got small distributed modular direct air capture, there are companies that might be interesting to at least get an idea what the technology is. I would imagine that steady power is going to be very important in any process engineering. And the idea of powering systems based on intermittent power seems a little bit challenging.
I think it's actually like there's another path. You can combine direct air capture with solar, and so the idea that I'm working on is basically creating a low voltage direct air capture unit that can be combined with solar, and it has like some internal heat storage, well insulated, so you can do intermittent direct air capture. Basically, you can, if you would like, you can put it in the middle of the desert and then create a fuel out of it or something like that, or put it somewhere else. So like I am interested in the very smallest scale of direct air capture, and like exactly the opposite of Carbon Engineering, the very biggest scale.
Yeah. What kind of scale are you looking at in terms of, I mean, even if you can thermally store heat, if your process uses heat, the heat's going to dissipate over time, and the sun's only available for a small number of hours per day.
Yeah, so the idea would be is that in that 8 hours of day you could do enough, and energy, solar energy is so cheap that your energy is almost free. So that's the basic idea. The idea would be a small modular unit, because it's so small, it only uses computer parts, and then it can store like a kilo. It can capture a kilo of carbon dioxide per day. That's like the idea. So it's very small, very modular, and then the idea is that like you can use this to build up bigger units, or if you're an entrepreneur interested in doing something with direct air capture, you can just use this unit. Or if you're a scientist and you want to do sorbent cycling, you can do this kind of things. And it's also something that other people are thinking about, such as the Open Air Collective that Ari Marder is part of, and I'm also helping a bit out with. So it's like the opposite of Carbon Engineering's idea, but also interesting. I think we need both, decentralized, centralized DAC.
Yep.
I'm actually
we
Carl,
got
really
a,
excited about distributed solar-powered water capture, and then you just use the water to grow plants, and that is a way of capturing carbon too. But I really think we need to have something seriously industrial scale. And yeah, I appreciate, I think, Rod's comment that if you're going to capture a lot of carbon, your system's going to look a lot like a refinery. And refineries cannot be turned on or off. They are continuous flow processes, and bad explosions and fires happen if you try to turn them on and off a lot. So you really want a reliable source of energy, and not wait for the sun to come up. So
we got a question in the chat box. So I mean, would you like me to read it and try to answer it? I'm just yeah, okay. I'm gonna go ahead. So
do it.
All right. The question is, I have a pretty basic question. What is advanced nuclear? What makes it advanced? Well, that's a good question, and an utterly fair question. And basically, nuclear power has been done the same way since inception for the last 65 years on a civilian power basis. And that way is by using a solid metal fuel and a water coolant. And water is actually not tremendously useful as a coolant. It's chemically unstable, and it obviously has a very low boiling point. So these modern designs are very different in the sense that they use different fuel forms and different coolants. So the system that we have designed, that we are now developing commercially, is a version of a commercial version of a so-called molten salt reactor. And what does that mean? And it means that the fuel itself, uranium, is liquid. It's liquid uranium, and it takes the form of uranium fluoride. So the uranium fluoride is a liquid at high temperature naturally, and it has a very, very high thermal phase range, roughly around 450 degrees C to 1400 degrees C. So it will stay liquid within that temperature range. And the coolant is the fluoride. And so what you have is a fuel and a coolant which are chemically bound together. Very, very, very difficult to separate. So the notion of a loss of coolant accident, which is a really bad thing in the nuclear world, does not exist in this kind of a reactor system. And it's because it's a fuel and coolant form which operate naturally at high temperature, they can make far greater use of the massive heat which is coming from nuclear fission, and that heat can be translated into industrial uses, as we've already been talking about. Some of the other factors that are happening in nuclear innovation are the size of the systems. So they're being made smaller. The typical conventional nuclear power station today is, gigawatt scale, 1,000 to typically 1,600 megawatts electrical. That is a massive, massive power plant, and they generally cost many billions of dollars to license and construct. So if you could make systems which are much smaller, ours is 200. Others are smaller, as Rod mentioned. There's companies out there that are developing commercial systems that are 1 megawatt, like batteries, which you fuel once and then you never have to fuel them again.
Yeah, I'd like to pitch in and say, that's kind of my definition of advanced, is something that incorporates the transistor. And the reason they built those big reactors because they're all highly trained, reliable human beings that had to be paid a lot and built by the world's best welders and such. And today we have CAD/CAM and we have automation. And so building 100 tiny reactors instead of 1 gigawatt scale one is actually cheaper and totally controllable. Then, so, you know, switching to the correct chemistry. The other thing is they just did it the same way they did for the submarine. And that light water reactor with water in it is a great choice for a submarine, because if something really goes wrong, one thing you can count on is it'll stay filled with water no matter what happens. You put that water-based reactor on land, suddenly keeping it full of water is hard and expensive and requires redundancy. So yeah, advanced for me also would mean looking at the physics books that have come out in the last half century and noticing that we've invented a lot of stuff like lasers and transistors and switches and tokamaks, and we have a lot of tools in our tool chest right now besides CAD/CAM and automation that we also haven't used. But Canon's totally right that this 1953 technology he's focused on is good enough to totally replace the energy industry. But there is other stuff out there, so it keeps getting better.
So I have a quick question that's for, I come from, I think, much less of a technical background than some of the other people on this call. But in terms of how nuclear applies to direct air capture specifically. So you talked about having, you needs to be able to generate enough waste heat to be able to cause the, not waste heat. Okay, so general heat to power.
Primary heat.
So primary heat, as you can tell, I already have extreme expertise in this. But to generate enough primary heat to power the DAC unit successfully. So first question is, what percentage of the current nuclear, I'd say American nuclear industry, or maybe broader nuclear industry, produces that level of heat? Is it all nuclear? Is it more of the advanced nuclear you're working on, how you described it? And
Yeah,
then, and second, to build on that is, if it is advanced nuclear in particular, how does that current market landscape look compared to the general nuclear landscape, which is a little complicated right now, from what I understand?
Yeah, the conventional nuclear system that we have today, there's about 440 nuclear power plants in the world. They cannot achieve a temperature greater than 300 degrees C. So that is not useful. I mean, you could use it to drive any industrial process you want, really, but it's not going to be thermally efficient, and it's not going to be cost effective. So advanced nuclear systems are, I believe all, I was going to say almost all, but I think they are all high temperature systems. So they have the capability of generating high temperature heat power at anywhere from, say, 500 to, say, 1,000 or even over 1,000 degrees C. So that's going to be way more thermally efficient for use in industrial processes like the chemical processing to separate carbon from the feedstock and so on. Some carbon capture processes themselves require a lot of heat, but mostly just power. And it's just a better way of making, cheaper way of making power. And it's a utterly reliable way of making power too, because it's on 24 hours a day for 100 years.
And so, what percentage of the nuclear industry right now is that in that advanced nuclear camp that can reach those temperatures and the rest? Just in terms of like applying DAC to this, like, is this a main thing or?
Yeah, and so in terms of commercial operation, that's 0%.
Got it.
So yeah, nuclear innovation is an emerging market. And the first commercial advanced nuclear power plants will be commissioned in the 2020s. In fact, there is one in Russia that exists right now. It started in 2017, but it was built and funded and operated by the government. But the civilian power market will see these advanced designs being licensed and constructed and commissioned in the 2020s.
Like, aren't there a lot of SMRs being built in China right now, or are they not active yet?
They are in the R&D phase. China is investing heavily in nuclear innovation, and they have a number of prototypes that they are building or have built and are operating. So yes, as a matter of fact, if I may say so, the Central Committee of China has 6 technological banners of national significance and one of them happens to be molten salt reactor. So this is very important for the Chinese government, and they are putting a lot of their resources into this R&D right now. But they don't have one yet, which is in commercial operation.
Well, they're claiming they're going to put some on warships so that their ships go twice as fast as American ships. And they also want to use them in power plants in the provinces that don't have enough cooling water for coal-fired or nuclear plants of the traditional design. So because of the higher temperature, you can do without cooling water entirely or use it very judiciously.
Yes, that's right. In a molten salt reactor and any of the other advanced systems that do not use water as a coolant, which is I think all of them, you don't need water. So I mean, it's cheaper if you do. You pay a small economic penalty if you use water for your power conversion system. In other words, making steam. But you can operate these systems entirely without water if you want to. So in places where there is no water, that can be very useful.
Yeah, or you can use them to provide desalinated water to agriculture at good prices, let alone for human consumption. There is no water shortage on this planet. It's just that some of it's too salty, and we know how to fix that.
Yes, that's exactly right. I think we can also use it to take carbon out of water, out of the ocean, which I think we all know that's a problem.
Well, that's an area that my former employer spent a lot of time and money looking at. I'm a retired Navy guy, and one of my last jobs in the Navy was working with the organization that was funding the Navy research labs to work on synthetic fuels. And for Navy applications, pulling CO2 out of water was a much better economic case because we had lots of water available, lots of ocean, and the concentration of CO2 was higher in water than it is in air.
And the ocean CO2 is more dangerous to us because the ocean might do something really catastrophic in 2035 to 2050 when the plankton changes its way of life. And that's a way bigger problem and way easier to understand than global warming. You don't need a modeling computer to figure out when still water turns to sparkly water and the plankton won't grow anymore.
Mm-hmm.
Rod, what was the reason that you needed to pull CO2 out of the water? What was the reason the Navy needed it?
Well, the Navy was interested in synthetic fuels. That was the idea of being able to go someplace and power your vehicles, airplanes, tanks, landing craft, without having supply lines. And when the case was made, or the analysis was made whether the CO2 should be pulled out of the water or out of the air, it turned out to be a better fit to pull it out of the water. It wasn't an environmental thing. It was about building a capability to create fuels on site in a theater without having logistical support.
Got it. Thanks. You know what, I'm gonna raise the issue that Dan James, who's on this channel, raised in the earlier conversation. We were talking a little bit about his situation where he's actually got a utility-sized property with connection to the grid and is looking to generate clean energy and can't make it work. And you know, it occurred to me that advanced nuclear was the perfect solution for him, but that in order to get started before advanced nuclear is available, that he could start with using the cheap natural gas, dirty energy that's available through the grid to try to start a carbon sequestration operation. and sell the carbon until he can then power it himself with clean energy. And apparently there's no market for carbon right now that's sufficient to pay for that kind of operation. So does anybody have any sense that there's any other markets, who's buying CO2 right now is really the question, if there is anyone.
I mean, people buying CO2 right now are, the greenhouses will often use it. They don't need super high concentrations of it. It depends how pure the CO2 amount is, right? There's always going to be some need for it in the beverage industry at much higher concentrations of purity. You start hitting pharmaceuticals and things like that. And then hopefully a market emerges of companies that take that CO2 and turn it into various products. But that's more than a few years away right now, unfortunately.
So
I think the
nobody's
key
doing
is-
synthetic fuels?
No,
No.
carbon engineering is doing
Yeah, but-
synthetic fuels.
They're working on it, but they're proposing a scale which is not really going to have an impact on the global transport sector. I mean, in 2018, the United States alone consumed 1 trillion liters of gasoline. So if you want to make synthetic fuels and have any kind of an impact on the decarbonization of the transport sector, you're going to have to be making basically billions of liters. You're going to have to be producing billions of liters of synthetic fuel per year from a plant, and that means millions of tons of carbon that you're capturing, and millions of tons of hydrogen. So those are the types of scales that we need, and the only way you're going to get that scale is with nuclear. I'm sorry, but that's an unavoidable fact.
So Canon, just why absolutely true. You need the nukes, can't get the energy density, buy all that stuff. Just curious as to what any particular characteristics of your plant that you think makes it better, because a number are doing, as you say, high temperature processes.
Yes, economics. We could deliver low cost power. We believe we will deliver power cheaper than any other form of energy. And it will enable these processes to be economic enough so that they can finally substitute for their fossil fuel counterparts. And that's never happened before.
Right, and that's economical, emission-free energy. Really cheap natural gas wouldn't help you because you're burning carbon to suck carbon out of the atmosphere. That's not going to work.
Yeah, I mean, every nuclear plant saves lives because we're currently killing about 4 million people a year with fossil fuel toxins. And so we can save 4 million people a year if we switch totally to nuclear. But I think, well, anyway.
I also think, interestingly, the lion's share of the CO2 market is for enhanced oil recovery. So that's just one of the funny landscapes for us to navigate.
Yeah.
The idea would be that's at least carbon engineering's idea is that with enhanced oil recovery, you can pump more carbon inside of the ground than you need for the oil. So you can have negative oil. I'm not really sure about that. I think another interesting idea would be to use aggregates. So if you look at the scale of aggregates, it's about 40 gigatons of aggregates per year that we use. So that would mean that if we could put the carbon inside the aggregates, we have more than enough storage there, and we don't need to put it under the ground, which psychologically doesn't add any value. But if you add it to an aggregate, the aggregate will actually grow. And it could actually be an interesting fit with nuclear. I'm not sure, perhaps because you have high temperature. Another thing, but that's, I think, down along the road later on, would be if you could create graphene, because you need high temperature heat. So then what you could do is direct air capture and straight on create a solid carbon out of it. I think with the current graphene process, they usually need high temperature heat, 600 degrees Celsius. So if you could make that, then you don't need any environment or environmental or geological conditions to store the carbon. You can just really store it in the middle of nowhere, and that's where the power of nuclear comes to light. So I think that would be a very interesting way forward, but there isn't a lot of research regarding large scale carbon out of the air to graphene. There's some liquid metal catalysts perhaps, but it's not well researched.
Well, pretty much all mineral processing needs high temperature heat. If you want to make solar panels, the right way to make them is with one of Terrestrial Energy's plants that starts off with 750 C heat. But I think for me, I've noticed that when we bring renewable energy online, it doesn't help because there's a lot of need for energy. And what matters is how much coal we shut down, not how much renewables we create. And the beautiful thing about, I think, and Canon hates this idea, I think, but if we can retrofit existing coal-fired plants to have a nuclear heat source instead of a coal heat source, it's not the cheapest way to build a nuclear plant, but it has the extra advantage of killing the coal plant, and it keeps all the political connections and the business connections and the workers busy. And so you end up reducing your carbon usage a lot. So that's how India and China can get off coal. They can't shut down the generation, but they can upgrade it to nuclear. And that could never happen with the old-fashioned kind of nuclear plant because 300 C isn't close to hot enough to running those turbines and generators.
Guys, we're gonna have another minute or two, and then we're gonna wrap things up.
Hey, keep in mind one thing: if we do see a change in U.S. president, that under the right circumstances, a huge amount of funding could come in to help advance nuclear. So that's something to gradually keep an eye on as we progress in the coming months.
Yeah, I mean,
I think it's likely to be the other way around.
Yeah.
I think
Well, you know, by the way,
green
Trump,
people that are going to do nuclear, not green.
Yeah, it depends who you talk to, which Democrat. But you're aware that the Trump administration stopped U.S. Department of Energy from cooperating with the molten salt reactor in Shanghai, from what I've heard.
Yeah, but that doesn't mean it's against advanced nukes.
Yeah, I don't think it wasn't a technological decision, but a geopolitical one.
Well, in my opinion, you're going to see a lot of opportunity, and this is not, I could be wrong, but this is not a time to be cynical, in my opinion.
Right. We've done public opinion polling, and both Democrats and Republicans like nuclear power. They don't like fallout clouds and waste problems. And I think Canon's solution does solve those problems in a convincing way.
Right.
So there's really not the opposition to nuclear power that people assume, even on the Democratic side. And we've done the polling to prove it.
All right, guys,
Look at Sheldon Whitehouse. Look at Senator Whitehouse working with James Imhoff on advanced nuclear. It's not going to be easy, but there are big opportunities. They'll be difficult.
Guys, I know this is a loaded part of the conversation, but I'm gonna have to end things here. Thank you so much, Canon, for proposing this topic. I posted in the chat the details for the next sessions. You can either click through one of those Zoom links, or if it's easier, I'll put the one that has everything on it. That last link will give you the titles of everything. You can click right from there. I could even share my screen if you'd like, if you want to see the graphic version of this. We're gonna jump into the new rooms, and then we'll do some like a kind of a 5-10 minute stretch and breathing break from there. So this room is going to be the room on, I believe, the biological carbon sequestration to products.
No, this is D.
Or decentralized. This is D. Right. This is decentralized DAC.
Room D. D.
I think there's okay.
Thanks for, just want to take
Thank you.
Thank everybody for participating in this. I enjoyed proselytizing, and I hope you'll all take an interest in nuclear innovation and want to look in it further. So thanks very much.
Thank you very much.
Thank you, Canon. That was
Thank
interesting.
you.
Yeah.
Good to see you.
Very good job.